Sorry, it was not audible. Sorry. So let us start again. So, an ordinary vector completely described by three sets of numbers, which are its three components in a basis of your choice. And a quantum state of a system, if you consider it as a vector in a vector space, you have to first describe it as a collection of numbers in an appropriate basis. So, suppose state of a quantum mechanical system described by the wave function psi at any instance of time. So, if you consider psi, which is a function of position vector r, as a vector, its component would be an infinite set of complex numbers, which would be the values of psi at all points of the configuration space. So configuration space is basically having three coordinates, position coordinates. Since in quantum mechanics, you mostly deal with functions, a vector describing the state of a quantum system is an infinite n-dimensional entity. So, while a quantum state cannot be described as an ordinary vector with three components, it is useful to describe a quantum state as a vector in complex vector space. So, earlier in this course, we have discussed how a quantum mechanical system, the state of a physical system is represented by a vector in a Hilbert space, which is a complex vector space with an inner product. So, we have discussed Dirac-Kate vector. Then we have discussed the notation and Dirac-Bra vector. So this is Dirac-Kate vector, and if you write this like this, then it will be Bra vector. And in Hilbert space, the set of all possible state vectors that describe a given quantum mechanical system form a complex vector space, which is called Hilbert space of the system and is denoted by the symbol H as shown in the screen. Are you getting it? So you can write, if your alpha and beta are represented by states, so alpha in Kate vector and beta in Kate vector are any two elements of H, then sum of alpha Kate and beta Kate will be sum alpha plus beta Kate, and it is also an element of H. So you can also write A plus B alpha Kate is equal to A alpha Kate plus B alpha Kate. Okay. So this is the Hilbert space representation, and superposition of two or more state vectors of the quantum system is also a state vector of the quantum system, and hence an element of the Hilbert space. So if psi1, psi2, so on, so forth, psi n are the states of the quantum system, then a linear combination of C1, psi1 plus C2 psi 2, so on and so forth, plus Cn psi n is equal to psi ket, which is nothing but summation I is equal to 1 to n Ci psi a, where C1, C2, Cn are complex numbers in a state of quantum system and a vector in the Hilbert space of the system. And this makes the Hilbert space a linear vector space. This L in a linear vector space. So what is a linear vector space? Anybody? Linearity is something related with straight line or having devoid of higher degrees. So the dimension of a vector space is the largest possible number of linearly independent vectors, and you can find for the vector space, if there is no such largest number, you can say the vector space has an infinite dimension. And a set of n linearly independent vectors, phi 1 ket, phi 1 ket, phi 2 ket, so on and so forth, phi n ket, forms a complete basis for an n-dimensional Hilbert space if every element psi ket of the vector space can be expressed uniquely as a linear combination of these states. So you can see in the screen, psi ket can be represented by C1 phi ket plus C2 phi 2 ket plus so on and so forth, Cn phi n ket. So this is an important thing, you know. It is expansion coefficient. Ci is called expansion coefficient, and Ci can be represented as C1, C2, so on and so forth, Cn. And psi ket is represented in a column matrix, and psi bra is represented as a row matrix, which we have discussed here. So see here, psi bra is represented as a row matrix, and psi ket is represented as a column matrix. And your bra vector is adjoint of your ket vector. Then inner product, we have discussed it in earlier classes.
What is bra vector?
Yes, this one is bra vector. You see here, this. In 10.2, you can see psi is represented in a bracket like this. So this is a bra vector, bra psi. And it is C1 star, C2 star, so on and so forth, Cn star. And here you can see it in this notation, psi ket, C1, C2, so on and so forth, Cn. And these two combined with each other, having an inner product, will represent a bracket in quantum mechanics in Hilbert space. Are you getting it?
Yes, sir.
So you can see in inner product, so you can see here alpha in ket and in bra is greater or equal to 0. It is bracket in bracket form. And a norm, you know,
left ket na bra?
Left is your bra, right is ket, bracket,
Inner product.
ket. Inner product is something different. I shall show you. This is a bracket notation. Inner product will be like this. Let us see it in somewhere else. Inner product. If alpha and alpha, the inner product will be like this. If there will be two things, alpha and beta and something else, then it will be in the example. You can see here somewhere. See here. This is also bracket, inner product in O cap operator. Okay, Q cap operator or O cap operator. And this is matrix representation of linear operator. Bra vector can be represented in a column matrix and in a row matrix, and ket vector is represented in a column matrix. Okay.
Yes, sir. Okay.
So you can see here. Then Hermitian and unitary operator. The self-adjoint operator O cap has the following property. Your O cap dagger is equal to O cap, and is in bounded finite space, a self-adjoint operator is also Hermitian, and in physical point of view, it is more commonly used term, and anti-Hermitian operator O cap can be represented as O cap dagger is equal to minus O cap. So Hermitian property, the function which obeys the Hermitian property is a physically representable quantity.
So
That
that is
which is
unitary
not
operator.
Hermitian. Yes.
Unitary means cap.
Unitary means the value will be I. Unit in a row format.
Yes.
1 1 1 1 1 in a row matrix. The value will be 1 in a 3 cross 3 matrix. 1 0 0 0 1 0 0 0 1. That is unitary. Okay. And orthogonal is if you multiply it, these two, it will give you 0. And orthonormal, it will give you 1. Are you getting it?
Yes, sir.
Then eigenvalues and eigenvectors, we have discussed it earlier on also. So you can see your A cap operated over psi ket will give you small a psi ket. So here you can see when A cap is operated over a state vector psi, which is in ket bracket, then it will give some value A multiplied by psi ket. So here A cap is a operator, psi is a state vector, and in the right hand side, psi is a state vector multiplied by A. So A is the eigenvalue. So when eigenvector is operated by an mathematical operator, say your position operator or momentum operator or energy operator, it will give you some value multiplied by that state vector.
So that is
So
state vector.
state vector here, it is psi is the state vector in CAD format. You see here. So this is state vector. When A cap is operated over this state vector, it will give some value multiplied by that state vector. Okay. Suppose it is position operator is here. When position operator is operated over a wave function psi, it will give you the position eigenvalue multiplied by that state vector. So what will be the position of that particular at a particular instance? You can have this from the eigenvalue of the position.
Sir, A is the position of A cap.
Suppose A cap is a generalized vector cap operator. Here you can put position vector, a position operator. If you put position operator here, it will give you position eigenvalue. If you put energy operator here, it will give you energy eigenvalue. If you will put velocity operator here, it will give you velocity eigenvalue. Unlike classical mechanics, where you will get exact value of a physical entity, here you will get eigenvalue of that physical entity because probabilistic nature of the wave function and the microscopic objects. Are you getting it?
Yes, sir.
Okay. So this is the characteristic equation. A cap psi minus A psi is equal to 0. 0 in CAD vector, null vector. So from this characteristics equation, you can also get the eigenvalue. Hermitian operator, eigenvector and Hermitian operator, it give a physical entity. Then eigenvector of commutating operator, you can have like this: A cap B cap psi n is equal to B cap A cap psi n. Not necessarily it will be always true, but if this relation will satisfy, then we can say that A cap B cap are commutating operators. Then unitary operator, which you are asking me, so you see this value will be 1. Okay. These things we have already discussed in earlier classes using differential operators or Schrodinger picture. But in terms of your Heisenberg picture, these are also very much important. Heisenberg picture, you have matrices, and this vector space will help you in solve those problems. So I think these are not being discussed earlier, or I have completed this in the earlier class. Then observable. What is observable and what is not? So there are some postulates. Every observable of a physical system is described by an operator that acts on the Ket vectors and that describes the system. So for a thing, for something or a physical system, anything will be observable, then it can be represented like this. Okay, this is the first postulate. Second postulate is if A is observable corresponding to the operator A cap, then the result of the measurement of the observable A for the physical system can only be one of the eigenvalue of A cap. If A cap is operated over the wave function or state vector of that wave function, if it will not give any eigenvalue of that A cap, then it cannot be an observable. Are you getting it? अगर उसका वैल्यू ही कुछ नहीं है तो कैसे ऑब्जर्व करेंगे आप उसको? So there must be some eigenvalue when A cap is operated over some wave function. Okay. Then postulates 3. When a measurement of an observable A is made on a normalized state, psi ket, the probability of obtaining an eigenvalue Aj is given by the square of the inner product psi ket with the eigenstate phi I of A cap, assuming that the eigenstates form an orthonormal basis. Okay. So here you can have A cap average. So it will be, see here, psi, then I cap, A cap, I caps, psi ket. So it will give you summation I from 1 to n, AI, psi, phi I psi square. So it will give you the average value. Then fourth, the von Neumann measurement postulate. If on measuring A for a system in a generic state psi ket, a result AI is obtained, then the state of the system immediately after the measurement is phi j. So you can see, suppose there is psi ket, then you measure it, measure of some value. Suppose A is your position or momentum or energy. Then the outcome will be A1, A2, AI2, AN. Anything from these can be the outcome. So the states of the system will be phi 1, phi 2, phi A, phi n in ket vector. This is the fourth postulate. Then compatible and incompatible observables. Compatible observables you can have if the operator A cap and B cap commute, which means that the commutator of A cap and B cap is 0. So in commutative bracket, A cap, B cap will be 0. Incompatible if it is not 0. Are you getting it? Then generalized uncertainty principle, which I have discussed already in the Schrodinger picture. So you can see here, in Schrodinger picture, we have defined uncertainty principle that you cannot measure with precision and accuracy two canonical conjugate variables. In this picture, in a Hilbert space, you can define it as for any two compatible observables A and B, del A, del B is greater or equal to 0. Therefore, A and B can be simultaneously measured with arbitrary precision. There is no restriction on the accuracy of simultaneous measurement. And for any two incompatible observables A and B, del A, del B must always be greater than or equal to positive definite quantity. So inherently, there is a limit to the accuracy with which A and B can be simultaneously measured. Thus, for every pair of incompatible observables, we have a Heisenberg-like uncertainty principle. So here is the Schrodinger picture in quantum mechanics, time evolution operator. You can see that the energy operator is I(h cross del by del t. So if you operated over some state vector, it will give you energy eigenvalue. Okay, which we have discussed earlier. In Heisenberg picture, you can see that A cap ht is equal to E cap dagger A cap ut. And if you solve it, then del A cap by del th is equal to U cap t dagger del A cap by del t U cap dagger. So this is Heisenberg equation of motion. Then you can choose the basis as per your convenience and according to the rules. Then there are some problems which you can solve in Hilbert space. Simple harmonic oscillator problem, which we have solved already in using Schrodinger differential equation. But here we can also solve it by using the Hamiltonian operator, that is P cap square by twice m plus half m omega square x cap square. So you can see here the formalism is somehow different. H cap can be represented as H cross omega A cap dagger A cap plus half, where A cap is equal to 1 by root over of 2 H cross M omega X cap plus I P cap, and A cap dagger will be 1 by root over of 2 H cross M omega X cap minus I P cap. So your H cap can be written as I have told you, A cap dagger A cap plus half. So it will be solved accordingly. Then you have the expectation value, which we have discussed in Schrodinger picture, and you can see here it also the same, n plus half H cross omega. Then creation and annihilation operator, lowering and raising operator, and eigenfunction of a simple harmonic oscillator, which we have discussed earlier, and you can see the values are same here also. Then uncertainty product, P cap square is equal to H cross M omega n plus half. The average value will be like this. Then angular momentum, we have discussed it in Schrodinger picture also. Your raging operator L plus cap is equal to Lx cap plus I Ly cap. Lowering operator L minus cap is equal to Lx cap minus I Ly cap. So by using the commutator relation, we will get different expressions, and your L cap square is equal to Lz cap square plus half L plus cap L minus cap plus L minus cap L plus cap. Then your eigenvalues of L cap square and L cap z can be evaluated as shown in the screen, and it will be similar to that we have evaluated using your Schrodinger wave equation. So you can see here your Jx cap Jy cap is equal to I H cross Jz cap, and Jy cap Jz cap is equal to I H cross Jx cap, Jz cap Jx cap is equal to I H cross Jy cap. So you can see the bracket Jx cap Jy cap Jy cap Jz cap Jz cap Jx cap. Similarly, J cap square Jz cap bracket is equal to 0. So angular momentum operator J and the physical significance we have discussed now. And this is your Hamiltonian your quantum mechanics in Hilbert space. Then spin angular momentum. You know, J cap is equal to L cap plus S cap. For J cap is total angular momentum, L cap is linear angular momentum, S cap is spin angular momentum. So you can have Sz cap is equal to H cross by 2 phi 1 bracket minus phi 2 bracket. Spin angular matrix for an electron, you can see here Pauli matrices. It is popularly known as Pauli matrices. Sigma x is equal to 0 1 1 0 in matrix format. Sigma y is equal to 0 minus I 0 in matrix format. Sigma z is equal to 1 0 0 minus 1 in matrix format. So this is very important in quantum mechanics. So spin has two states, spin up and spin down, and this can be represented as shown in the picture. So Pauli spin matrices are anti-commute. So your bracket psi I psi j is equal to 0, where I comma j is equal to x y z, and the trace of each Pauli matrix is 0. The square of each Pauli matrix is the identity matrix psi I square is equal to I, where I is equal to x comma y comma z, and L is the 2 cross 2 identity matrix. And the Pauli matrix follow the commutation rules. So your if you commute sigma x, sigma y, the two components of Pauli matrices, it will be 2y sigma z. And if you commute sigma y, sigma z, it will be 2y sigma x, and sigma z, sigma x will commute. And the commutation rule will, if you put sigma z, sigma x in bracket, commutation bracket, you will get 2y sigma y, where sigma x, sigma y, sigma z are Pauli matrices. So Pauli matrices are used to represent electrons. Then the electron wave function, your psi of defines the probability of locating the particle at the point x in the spin-up state. That is the z component of the spin angular momentum is h cross by 2, where the psi down defines the probability of locating the particle at the point x in the spin down state. That is the z component of spin angular momentum h cross minus h cross by 2. So electron is described by two component wave function in the coordinate basis. Then your magnetic moment. So classically, L vector is equal to M R cross V, which is equal to MRV K cap. But quantum mechanically, your mu L cap is equal to minus E by twice M L cap. So it is completely different. And it is also quantized. And spin magnetic moment, you can see, is also different from classical picture. So Goudsmit and Uhlenbeck advanced the hypothesis according to which every electron rotates with an angular momentum h cross by 2, which is the spin angular momentum, and carries in addition to its charge a magnetic moment equal to Bohr magnetron, which is mu b. And mu b can be represented as E h cross by 2 me. And this intrinsic angular momentum is not due to the rotation of the electron of the about its axis, rather the magnetic moment due to the spin angular momentum is actually mu s vector is equal to minus g by twice m s vector, where g is nearly equal to 2.0023, that is lambda g factor, and E is the electronic charge, and s vector is the spin angular momentum vector. So the z component is shown in the screen. Then Stern-Gerlach experiment. This is very important. The experiment, originally conceived by Otto Stern in 1921, was carried out by him and W. Gerlach in the year 1922 in Frankfurt, Germany. The experiment was designed to verify the notion of space quantization, that is the quantization of z component of angular momentum of electron as proposed in the Bohr-Sommerfeld model. Silver atoms are heated in an oven in which here is a small hole through which the silver atoms escape. The beam of silver atom is passed through a collimator and then enters an inhomogeneous magnetic field produced by a pair of pole pieces. The standard experimental arrangement is shown in the screen. You can see it. So here there is a source for silver atom, then collimator, then magnet. Then the screen you can see. One in the up, one in the down. So classically, magnetic moment for a silver atom, suppose it is mu, the force is silver atom is F, which is nearly equal to mu z del B z by del z, which where mu z is the magnetic moment of atom along the magnetic field. But it will fail to explain the phenomena. But quantum mechanically, magnetic moment of the electron originates from its orbital motion. In the quantum mechanical picture, you know, Lz is quantized and therefore so is mu z. Then the angular momentum eigenstates, which are simultaneous eigenstates of L cap square and Lz cap, are characterized by the values of L and ml respectively, where L takes an integer value, and for each value of L, ml has 2L plus 1 integer values running from minus L to L. So you can write mu z is equal to minus EH cross by twice ml, and it has discrete values corresponding to the discrete values of ml. In keeping with the idea of quantization of orbital angular momentum, a single beam of atomic dipole will split into 2L plus 1 beams corresponding to the 2L plus 1 values of ml. So L has integer value, so 2L plus 1 is always odd. However, in the experiment with silver atoms, the number of traces is an even number, that is 2. Stern and Gerlach also measured distance between the traces and concluded that the values of ml does not change by 1. So the valence electron in the silver atom is located in the SL. For this electron, L is equal to ml is equal to 0, and the magnetic moment in the z direction is also 0. So if the angular momentum of the electron is only due to its orbital angular momentum, the silver atom should not be deflected at all by the magnetic field, and there should be just one trace, not even two. So while the Stern-Gerlach experiment showed that z component of the angular momentum was quantized, and that the angular momentum component in the direction of magnetic field changed in the integral multiple of h cross it could not shed light on the origin of the magnetic moment. So here you can see there are two, spin up and spin down, but the origin is unknown. With the introduction of the idea of spin angular momentum of the electron, even with L is equal to 0, the electron has a finite angular momentum in the z direction due to its spin angular momentum plus minus h cross by 2. And the two possible values of the magnetic moment which causes the deflection of the silver atom in the magnetic field leading to two traces. With this, it seems reasonable to introduce four quantum numbers n, that is your principal quantum number, L, Ml, and Ms for the electrons. The eigenvalue S cap square is S into S plus 1 h cross square, where S is equal to half, and the eigenvalues of Sz cap are Ms h cross, where Ms is equal to plus half or minus half. Then sequential Stern-Gallagher experiment, you can have the source, then A, spin up, spin down, then spin up, spin down, then spin up, spin down. So in the z direction is not special in any way, and the eigenvalues Sx and Sy cap are also h cross by 2 and minus h cross by 2. The two beams observed in the experiment therefore corresponds to spin up state or in the spin down state of the Sz cap vector. Sz cap. Okay. So an electron at rest in a magnetic field in the z direction, B vector can be written as B0 k cap, and the Hamiltonian for the electron is H is equal to H int superscript S is equal to minus mu S vector dot B vector is equal to minus mu Z vector B0. So mu Z is equal to minus GE by twice MSZ, where SZ is equal to H cross by 2 or minus H cross by 2. And by using G is very small, near than 2, is approximately 2, you can get mu Z is nearly equal to minus E by M Sz, and H cap into superscript S is equal to Hamiltonian of electron is equal to E by M Sz cap B0, which is nothing but EB0 by M Sz cap, which is equal to mu 0, omega 0, sorry, omega 0 Sz cap. So for an initial state psi 0, the final state of the system will be psi t ket is equal to e to the power minus ih cross ih cap t by h is psi 0 is equal to e to the power minus I omega 0 sz cap t by h cross psi 0. Okay, so this way you can evaluate it. So you can see here there is a very beautiful example. You can write the SY state in terms of eigenstates up and down. Considering the Stern-Gallagher experiment with the uniform magnetic field in the z direction, you can calculate psi ket, assuming that the initial state psi 0 ket is equal to cos alpha of plus sin alpha down. So you can see here. If you have any doubt, you can ask. You can see here the solution is here. I have shown in the screen. Okay, so you can see here. If you have any doubt, you can ask now. I think it is visible. So you can see here. So next you can have something which you need to know. Let us have this. This we have already discussed, but let us have a I discussed these things. So, how your Davison-Germer experiment and quantization, you can see all these things. We have discussed it earlier. Your complementarity in Hilbert picture, in Hilbert space, in Heisenberg picture, we have discussed it today. And in Schrodinger picture, we have discussed it earlier, and let us again discuss it. Position and momentum measurements are really complementary and they are mutually exclusive processes. And Heisenberg uncertainty principle is applied to it. And Heisenberg uncertainty principle is clearly a consequence of wave particle duality. There are some examples we have discussed it earlier. Probabilistic interpretation, Max-Born interpretation, we have discussed it in the earlier class. Then acceptable solution of the Schrodinger equation, psi x should be finite and single valued everywhere, should be square integrable. Both psi and d psi by dx should be continuous everywhere. The acceptable solution of the time independent Schrodinger equation exists only for certain discrete values of the total energy E. Thus, energy quantization is an inherent property of the Schrodinger equation for the bound state. Then quantum mechanical operators. This is very important. We have discussed it earlier and today also. So, what is an operator? You are familiar with the notion of function in mathematics. The function is a rule for changing a number into another number. Suppose you have two numbers, 3 and 5. If you put a plus mark in between, 3 plus 5 will give you 8. So here is an operation, addition operation. 3 is added with 5 and it will give you 8. 3 plus 5 is equal to 8. Similarly, operator is something like that. And it is a rule that turns one function into another function. Okay, if an operator is applied to a function, you get a new function. When 2 and 3 is added, it will give you 5. When 3 minus 2 will be subtracted, it will give you 1. So the two numbers are same, but the operation will decide what will be the outcome. Similarly, depending upon the nature of the operator, your new function, what will be the new function, it will be decided. Okay, d by dx is an operator and it will give you the derivative of fx. Okay, so suppose there is a function fx is equal to 2x square plus 3. So alpha fx will be how much? 2 alpha x square plus 3 alpha is equal to gx. Okay, x square plus fx is equal to how much? 2x to the power 4 plus 3x square. It is a new function hx. dfx by dx will be how much? It will be a new function px, that is 4x. So there are some quantum mechanical operators and it is somewhat different from this type of algebraic operators. So you can see in classical mechanics, the dynamical state of a system is determined at each instance of time. It is determined by knowing certain physical quantities such as position, velocity, linear momentum, angular momentum, energy, etc. of a particle constituting the system. These are the dynamical variable of the system. The dynamical variables associated with a system can be measured and provide information about the system at a particular point in space and time, in space-time. In general, such measurable quantities that describe a physical system are called observables. In classical mechanics, every observable is associated with an operator in quantum mechanics, which operates upon the wave function of the system. So in quantum mechanics, an observable that corresponds to a physical quantity such as energy, spin, momentum, position is associated with the corresponding operator, which I have discussed earlier on. So there are postulates of quantum mechanics. Every physical observable is associated with an operator which acts on the wave function. And there is parity operator, psi minus x is equal to psi x when psi x is having even parity, psi of minus x is equal to minus psi x when psi x is of odd parity. Okay. Then operator obeys commutator algebra. So within bracket, a cap b cap will give you minus a cap b cap. So it will not commute. A cap b cap c plus c cap is equal to a cap b cap plus a cap c cap. A cap b cap dot c cap is equal to a cap b cap c cap over in bracket plus a cap c cap multiplied by b cap. And a cap b cap c cap is equal to b cap a cap c cap plus a cap b cap c cap as shown in the screen. Any operator always commute with its own power. A cap to the power n, a cap over bracket will give you 0. C cap, a cap over in the bracket will give you 0. Then a linear and antilinear operator. Okay. If a cap phi plus psi is equal to a cap phi plus a cap psi, where c is an arbitrary complex number, you can combine a cap lambda phi plus mu psi is equal to lambda a cap phi plus mu a cap psi, where lambda and mu are complex numbers, and these are linear operators. And you come across another type of operator in quantum mechanics, that is antilinear operator, which have the following property: a cap lambda phi plus mu psi is equal to lambda star a cap phi plus mu star a cap psi. This is antilinear operator. A cap is the antilinear expectation value, as I have told you earlier in the Hilbert space. We have discussed it, and here also average value of psi is equal to integration minus infinite to infinite x fx dx. In eigenfunction and eigenvalue we have discussed in the first class. The non-phase theorem. So what is non-phase theorem? For a macroscopic system, there is hardly any difference between x, px, and dv by dx and their average values. However, for microscopic system, they are quite different. As a matter of fact, you have seen that for a microscopic system, the precise values of x and px do not exist simultaneously, but their average value can be obtained. So the equation dpx by dt is equal to minus dv by dx, where v is a function of x, and derivative of dt, px average will be minus average of dvx by dx. So this type of thing, and derivative of dx average of x is equal to 1 by m px. These two expressions will constitute the on-phase theorem, which shows the correspondence as well as basic difference between classical and quantum mechanics. So on-phase theorem you can see in the screen. Derivative of dt, average value of x is equal to 1 by m average of px, and derivative of dt average of px will be minus average of dv by dx. Okay, and the applications we have discussed in the first class. If we say, then we can also recapitulate it. Okay, we have discussed simple harmonic oscillator, hydrogen atom, and 1-to-1 3-dimensional and symmetric potential problem. Okay, so if you have any doubt, you can ask. Otherwise, you see this very good problem there is in your course material. The problem is like this: an operator, the eigenvalue and eigenfunction of a quantum mechanical operator a cap are denoted by an and psi n respectively. If fx denotes a function that can be expanded in the power of x, so that f a cap psi n is equal to f a n psi n. So the solution is here in the screen. Here you can see it. And there is another problem. So that within bracket h cap px cap n to the power n is equal to I n h cross px cap to the power n minus 1. If f px is a dynamical variable which can be expanded in powers of px, you can have over in the bracket x cap F cap Px cap is equal to IH cross del F by del Px cap. And another very important problem, the normalized wave function for a particle of mass m is psi, which is a function of x, can be represented as 2 alpha by pi to the power 1 by 4 e to the power minus alpha x square for x between minus infinite to infinite, and to calculate the expectation value of the kinetic energy of the particle. So first see the first problem, then I shall show you the second problems, worked out problem shown in the screen. Okay, you see, if any doubt, you can ask now. You can see here the solution of the second problem. Okay, so there are some important problems also. So far as your application of quantum mechanics is concerned. So let us have some of them. So here the problem is, use the uncertainty relation to show the dimension of the most stable ground state hydrogen atom is of the order of the first Bohr radius A0. You can see here in the screen. So you can write d by dt is equal to dv by d theta, d by dv is equal to minus sin theta d by dv. So from that you can have it. Here it is. The solution is here. Let the eigenfunction be psi r theta phi is equal to r theta y theta phi. So h cap is equal to L cap square by 2L. So steady state Schrodinger equation is equal to h cap psi E psi, and you can use the relation to prove it. Uncertain relation to prove it. Here it is. The problem is use the uncertain relation to show that the dimension of the most stable ground state hydrogen atom is of the order of the first Bohr radius A0, and it's shown in the screen. Let the size of the atom be R0. Since the electron is inside the atom, the uncertainty in the momentum is P is equal to h cross by R0. The linear momentum magnitude P can be in any direction, so its component can have values from minus P to P. Hence, the uncertainty in momentum is also approximately P. Hence, we can take del P is equal to P. So your average value of kinetic energy will be del P square by 2 mu is equal to h cross square by 2 mu R0 square. And your energy will be kinetic energy plus potential energy, that is equal to h cross square by 2 mu r0 square minus e square by r0 square at r0. So your d by dr0 is equal to minus h cross square by mu r0 cube plus e square by r0 square, which is equal to 0 for a stable atom. So your r0 can be written as h cross square by mu e square is equal to a0. So the size of the most stable atom is the first Bohr radius. Okay. And the next problem is obtain the most probable value and expectation value of R for the ground state of hydrogen atom. So the solution is like this. You can see here the probability of finding the electron between R plus dr is given by psi 100 R modulus is equal to R square 4 pi dr, and it is equal to 4 by a0 q R square e to the power minus 2R by a0 dr. So most probable value of R we can evaluate average and the average value. So most probable value will be a0 and average value will be 3 by 2 a0 as shown in the screen. You can have it. If you have any doubt, you can ask. So you know deuterium is a stable isotope of hydrogen with a proton and a neutron in the nucleus. So for this, you can have another problem. Given that the reduced mass of a deuterium atom is 9.106909 into 10 to the power minus 31 kg, calculate the ground state energy. Okay, so you can use the equation here, that is E1 is equal to minus 9.106909 to the power into 10 to the power minus 31 multiplied by 2.31 into 10 to the power minus 31 square divided by 2 into 1.054 into 10 to the power minus 34 square whole square in joule, and it will be equal to 13.67 eV or 21.87 into 10 to the power minus 19 joule. So there is another problem. Consider an electron in the state psi, which is a function of position vector r, is equal to n multiplied by psi 100 plus 2 root 2 psi 211 minus 4i minus 4i psi 21 minus 1. So determine the normalization constant C and the expectation value of the energy of L cap square and Lz cap. So it is shown in the screen. You can go through it, and if you have any doubt, you can ask. So I think it is clear to you. The value will be minus 16 by 25 h cross Lz cap and Lz square will be 48 by 25 h cross square. So I think it is clear. Then let us have a hydrogen atom like problem. Okay. So you can see the wave function for the hydrogen atom in the hydrogen, the wave function for the electron in the hydrogen atom is psi of psi, which is a function of position vector r, is equal to 1 by 6 3 psi 200 plus root over of 7 psi 211 minus 2 psi 21 minus 1 plus 4 psi 311. So you can calculate the expectation value of L cap square and Lz square as shown in the screen. Your L cap square, average value of L cap square will be 3 by 2 h cross square, and average value of Lz cap will be 19 by 36 h cross, and the solution is shown in the screen. Okay. So I think it is clear to you. So hydrogen atom problem we have discussed, already discussed. So here is, you can see average value of R square for the ground state of the hydrogen atom. So it is evaluated here. I have shown you earlier this also. So you can see here, it is 3A0 square. Psi 100 is equal to 1 by root over pi A0 Q e to the power minus R by A0. So R square, average value of R square will be 3A0 square as and the problem is solved as shown in the screen. Is it clear? So if you have any doubt in any step, please ask. Let us have another problem. Obtain the most probable value and expectation value of R for the ground state of hydrogen atom. So the problem is solved and is shown in the screen. Average value of R is equal to 3 by 2 A0. So if you have any doubt in any intermediate step, you can ask. Am I clear? Okay, I think it is clear. So these are all about the applications of quantum mechanics, and these are of utmost importance, as you can see in those classes, in these classes. So we have discussed application of quantum mechanics for a potential state or a potential well, or simple harmonic oscillator, one dimensional and two dimensional cases, spherical symmetric potential, its application to hydrogen atom, and other things. Box, particle in a box, so on and so forth. So I think it is clear to you that how quantum mechanics is very much important in microscopic world and for the dynamics of electrons, protons, and similar type of particles in an atom, in a molecule. Quantum mechanics will be very much helpful. So thank you all for your patience hearing, and if you have any doubt, you can ask.